Okay. Um, sorry. This is a little long. Yeah? Let's write back. Okay. If you remember that during the linear classification, what actually you learn is that now the equation is not linear anymore. Now the equation is represent your hyperplane. So what is meaning by hyperplane there is that the equation now is not represent the relation between the input and output, but the equation there represent the border that can classify between whether that points belong to class 1 or class 2. That is if we talk about the binary classification. So that's why actually this linear classification, or another name for linear classification, is logistic regression. Is a standard version of linear regression, or a standard version of uh, linear regression here. So that's why during our linear regression, that is your equation there, theta y equal the predicted y is there, or y hit there is equal to theta naught plus. So okay, so your y head is equal to theta naught plus theta 1 theta 1 x1. So up until theta d xd. So, or in other words, um, is actually is theta naught plus the summation of your theta 1 x1 where I equal to 1 up until your d. Okay, but in um, linear classification, it it's actually is a standard version of this equation. Is actually your predicted y, or y it is equal to the sigmoid function. Okay, the sigmoid function of so y is equal to 1 over plus exponent to the power of negative v here, where actually v is the linear equation of is the same linear equation as before, theta naught or theta 0 plus the summation of your theta 1 x1, so I equal to 1 up until d. So that is the equation there. So this is what I mean by cascading. You can see that if I draw the block diagram, okay, it seems to be if you talk about linear regression, so the input is x. Okay, it's a whole x there. Means that the whole x you have here is a whole x, a vector. Means you have the x1 up until xd. And here we use a symbol, a summation represent this operation, the linear operation here, to get your y hit. Okay, so to get your y hit in linear regression, okay, the process is just a weight sum, a summation of your product between the x and w, or x and theta in this case. So that's why I'm using this equation that represent this operation, the linear operation. That is linear regression. However, for linear classification or logistic regression, what have been extended is that you are using the same x, the bold x there, is we're going into two blocks. One is the, uh, the, the linear function, which is this one. And then once you produce v over here, it will go to another block, which is your non-linear function. I just put it as f. Actually, f is your logistic regression, this one, before you can have the predicted y. So you can see that this is linear. This is linear regression. This is a linear classification. Okay, during the lecture 5, we talk about this one. During the lecture 6, we talk about this one. Okay, means that you have the x, and then x will go to the proceed to the linear this linear equation to produce v, and then this the output from the linear function here will go into this f, which is as a non-linear function to produce y. So in and in this one is we have discussed in lecture 6, where we you have been exposed with two type of f here. This one is sigmoid function, and then the last part, when you want to do a multi-class classification, you have been exposed into softmax functions. Okay, just change this f, it become multi-class classifier. If you are using a sigmoid over here, it become a binary classification. So that is what I'm meaning by cascade here. Okay, before this you have this kind of process, but if you want to change your linear classification, I'm sorry, linear regression into linear classification, you are cascading another function here before you can get you are cascading another function here with your existing function before you can get the predicted y or y hit over here, because in order for you to change from regression into classification, you need to add one non-linear function to represent that. Okay, so that is the difference between linear regression and linear classification. And in this case, I think I don't know whether this one have been discussed before. Another f that you can put here instead of sigmoid and softmax is called sine function. I think this is also in lecture 5. Before we discuss about sigmoid, which is better than sine function, we first introduce with sine function, and remember the sine function is something like this. You have okay, if the v there is negative, then they become -1. If v here is positive, then this y will become positive value. But because the transition is very hard here, so we want to make sure that you have a smooth transition. That's why sigmoid function have been introduced, where the transition here will have some a little bit curve. So this is sigmoid. So that is the difference between sine function and sigmoid function. So you can see that if you talk about linear classification, yes, we can. And if you talk about linear classification, especially a binary classifier where you only can provide the y into two classes, then you can choose either sigmoid or sinc function. So this is related to sinc function. Okay, you can see that if you find your f here, which is actually this one is related to this one, the 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 v there. Okay, v. If your v is more than 0, then your predicted y become +1. If your v there is less than 0, like this, okay, this one, then your predicted y is equal to -1. So this is one of the example, one of the basic example of fundamental example for linear classification, which is using the uh, the, the non-linear function, which is the sine functions there. but of course you already learned a lot, you know, okay, because this one is the basic one. Of course there's a disadvantage of using this sync function. That's why people try to extend this one. Instead of using a sync function, you are using a sigmoid function, because the transition there is very smooth. Instead of you decide a very hard decision there, it's because the sync function only provide is it should be either minus one or plus one. It's not good to have that transition, that hard decisions there, hard transition there. But for sigmoid function, you have a transition where you can choose. There's a certain value where actually there's a value that might close to positive one, and some value that might close to uh, negative one. Okay, that transition later you can see it will provide you how strong that point is close to class A, and how strong that point is close to group B, for example. So we want to have something like that, which is better than just to have a hard decision as a sign function here. You are directly choose either is belong to class 1 or class 2. I'm sorry, class minus 1 or class positive 1. So that's why sigmoid is better, because you have a transition there. And there's another, later we discuss what is another advantage of using sigmoid function as compared to the sign function there. Okay, and then again, I think this is the same. Okay, um, in linear classification, uh, what to your objective is you want to find the weight that can minimize the cost function, and then how to do that, you can use the MCE, mean square error, to find the minimum point among that cost function. And then once you find the minimum point, then that is actually the optimum weight that can fit into your data. Okay, just that is how we do. And again, don't confuse with what have been done before. You can see that what you have done before, once you go, okay, if you remember that during the previous lecture, okay, when you learned the linear model for regression, when you want to optimize your cost function or minimize your cost function to find the optimum theta, you use the gradient descent, but the cost function, when you want to get during the when you learn the linear model for regression, you define your cost function as mean square error. Okay, but when you learned um, linear model for classification, your cost function is actually a cross entropy, or the the maxim that maximizing the what we call as a maximum likelihood estimation, which is the J here is defined as this expression. Okay, actually, if you refer to um, many textbook, you will find out, even let's say if you want to do a classification, you still can use the MSE here. Okay, means that MSE is not specifically for regression. The MSE also can be used for this case, but of course, the as compared to MSE, the cross entropy is better in terms of in minimize the cost function that related to classification model. Okay, but this does not mean the MSE definition here cannot be used at this part. You can also um, apply the MSE at this part, but in this lecture we try uh, to provide or expose to you to another cost function which is suitable to be used for classification cases. But that does not mean the classification need to use this one. You can also use the MSE. Just the MSE is not better, is not good as compared to um, to maximum likelihood expression here, because this one will give a lot of benefit in terms of uh, in finding the optimum function very fast as compared to the mean square error in classification model. But later, but in my lecture later, you will see that I'm even for classification in neural network, I'm using this cost function because I don't want to expose to too many a technique or too many approach in minimizing the cost function. So that's why, because even the neural network itself is very big and complicated, so I just reduce the scope there instead of we are exposed into several technique in minimizing the cost function. One is MSE, another one is maximum likelihood. Then for my material, I only my the scope is only UI. Doesn't matter is it classification or regression. We will use the mean square error. Okay, MSE, and even you will see that there's a little bit different as compared to the previous lecture in terms of how to define the gradient descent, in, especially in finding the, the in finding the optimum W to get this function. But in my material, most of the time I will use this approach in minimizing my cost function.